Right, today we are learning about thin cylinders. What is a thin cylinder? How can we define what is a thin cylinder is? Now we are not going deep into the term what is a cylinder is. We are talking about some vessels which are used in some boilers, turbines where we have very high temperatures involved. There we need to have some closely packed vessels because we can't take any considerations of leakage of pressures there, so we need very closely packed vessels. So there we need to use cylinders which can withstand high internal pressures. We are considering cylinders which can withstand high internal pressures. Then the term comes here is thin, because these closely packed cylinders, the thickness is very small when compared to the internal diameter. So it is very small when compared to the internal diameter of the cylinder, the thickness value. So that's why they are termed as thin. If you are talking about the number point of view, if the thickness is less than 1 by 15 to 1 by 20 times the diameter of the internal diameter of the cylinder, then it is defined as thin cylinder. If the thickness is less than 1 by 15 to 1 by 20 times the diameter or internal diameter of a cylinder, then it is termed as thin cylinder. Okay. Now, as we mentioned that the cylinder should undergo or should withstand high internal fluid pressures. It should withstand high internal fluid pressures. That means the fluid which is passing inside the vessel or the cylinder will create some high pressure, then the cylinder should withstand it. There may be also a chance for the cylinder to fail. Now we should find out how many ways we have or the cylinder can chance to fail. There are usually two ways of failure. One is along the circumference of the cylinder. The second one is along the length of a cylinder. What exactly happening is the internal fluid pressure which is inside a cylinder creating a burst force or bursting force. I think you know what is a burst is. It will burst. If the bursting force is along the circumference, we define it. The failure is along the circumference. If it is along the length, the failure is along the length. That means, see, if this is a cylinder, right? Now, if the failure is along the circumference part, that means it is along the circumference part. That means the force or the bursting force is acting about vertical or perpendicular form, upside and downwards, upwards and downwards, then the failure is along circumference. If not that, if the same cylinder in which the bursting force is along the length, if it is along the length which is horizontal or in a way parallel, then the failure is along the length. That means in this, our cylinder will get aparted in this way, the two halves. Here the cylinder may get aparted in this way. This is along circumference and this is along our length. If the circumference part will gives rise to a stress called circumference or hoop stress. Circumference or hoop stress, some sigma 1 or sigma c or sigma h. This along length failure gives rise to longitudinal stress. Longitudinal stress, some sigma 2. This is circumferential or hoop stress. This is longitudinal stress, some sigma 2, right? Now we should find an equation for both longitudinal and circumferential stress, finding a relation for them, for both stresses. Before going that, we need to remember that here we have two forces acting. One force due to internal pressure or the bursting force. Second one is the resisting force. Obviously, if there is a force which is trying to burst the cylinder, there will definitely, by virtue itself, it will definitely have some resisting force. We are assuming that these both forces are same, right? 1 is equal to 2. For a safe design, these both should be equal for a safe design. Now we'll see for both stresses. The first one is circumferential or hoop stress. And we know that here the failure is along the circumference of the cylinder. Failure is along the circumference of the cylinder. Okay. Now the first force, which is force due to internal pressure or the bursting force, okay, will actually, any pressure force or any pressure will be equal to, if you see any pressure is equal to force by area, then force will be equal to pressure into area. The same force is equal to, now we are talking about some internal pressure, I am assuming it as some P into area. Okay, P into, as here the failure is along the circumference, we write it as the diameter of the circumference of and the total length of a cylinder, which is P into D into L. This is our first force, which is internal pressure. Second one is the resisting force, which is opposing the bursting force, right? The resisting force, due to this force we are having the circumferential stress, because we know what is the stress, right? How can we define a stress? Stress is simply resisting force per area. We defined long back what is the stress actually. So this is our circumference stress. The circumference stress is obtained, or you extracted it by this resisting force. So now we know stress is equal to load or force by area, then force is equal to stress into area. So now this resisting force is equal to some stress, circumferential stress, into our area part, which is also along the circumference. Here we have length into thickness. Here we are considering the thickness, but we have two parts, right? If you see the diagram, here you have 1 and 2, you have 2. So this is length into thickness plus length into thickness. So finally we have sigma 1 into 2 into L into T. What we said, to have a safe design, we should have both the forces equal. That means our P into D into L, the first one, is equal to sigma 1 into 2L into T. L cancel. So L cancel. This is T, okay? L cancel. Now sigma 1 is equal to, here you have PD. This is 2T. We bring here. Now circumferential or hoop stress equation is PD by 2T, where P is our internal pressure, D is internal diameter of the cylinder, T is thickness of a cylinder. This is circumferential or hoop stress. The second one is longitudinal stress. Which is some sigma 2. Sorry. Here failure is along the length of a cylinder. Failure is along the length of a cylinder. So in the same way, here also we have two stresses. One is the internal stress due to internal pressure or the bursting force. The second one is resisting force. We should equate them both for the same safe design. So the first one, which is force due to internal pressure, or we simply write it as some burst force. We already explained that pressure is equal to force by area. Force is equal to pressure into area. So force is equal to pressure into area. Pressure into, here area is pi by 4 d square, because it is a cross sectional part. If you see the diagram here, I am mentioning you, if this is a cross section, you will have a circular part. So cross section of a circle will be obviously pi by 4 d square. So the area is here pi by 4 d square. The second one is resisting force, the force which resists the internal pressure or the burst force. And I already said you, due to this resisting force we having a stress, because stress is equal to resisting force by the area. So due to this resisting force, the stress we obtained here is longitudinal stress. This longitudinal stress is equal to resisting force by area. Resisting force is equal to stress into area. So now the resisting force is equal to stress into area. Stress into pi d is our circumference, into the thickness part is this. Now we should equate these two to have a safe load. So pi by 4 d square is equal to sigma 2 into pi d into t. Pi d cancelled. Here it is p into d by 4, bringing this thickness here. So sigma 2 is equal to, or longitudinal stress is equal to pd by 4t. These are two basic stresses we have. We also have another thing called shear stress, or the maximum shear stress value. And we know these both stresses, where this longitudinal stress and the circumferential stress are acting in the principal planes. Both are acting in the principal planes. Now the shear stress or the maximum shear stress value can be obtained as sigma 1 minus sigma 2 by 2. This is from the theories of failures which we already learned. So this is pd by 2t minus pd by 4t by 2. This can be pd by 8t. Now the Tmax or the tau value, tau max, which is the shear stress or the maximum shear stress value, is pd by 8t. So now we are done with the three stresses, which are namely, first one is circumferential or the hoop stress, which is pd by 2t. The second one is longitudinal stress, which is pd by 4t. The third one is shear stress, which is pd by 8. Now we are going to the next topic, which is finding the effect in dimension of the cylinder due to internal pressure. Due to the internal pressure or the bursting force we having inside the cylinder, there may be a chance for the cylinder to be affected in the dimension way, means there should be some change in the dimension. So from this concept we have strains, which are obviously two. One is circumferential strain or hoop strain, circumferential or hoop strain, which is E1. Second one is longitudinal strain. Which is E2. As I mentioned again already previously, circumferential is something which is along the circumference of the cylinder. This is along the longitude of a cylinder. First we will see the circumferential part, and then we will go to the longitudinal thing. Circumferential strain or hoop strain. So we are finding a relation for the circumferential strain or the hoop strain value. We know we have two types of strains, or basically there are linear strain and the other one is lateral strain. This linear strain is along the parallel direction of the force we are applying, and this is the perpendicular direction of the force we are applying. We know there is a ratio called Poisson's ratio, which is a ratio of this lateral strain to linear strain. Okay, now for finding this circumferential strain, E1 is equal to, I am going to write an equation here, sigma 1 by E minus mu into sigma 2 by E. How we got it? It is a very simple equation. Now, you know, Young's modulus or the modulus of elasticity is equal to stress by strain. Now the strain is equal to stress by modulus of elasticity. So we are done. Then how come this is Poisson's ratio is mu? So if we want the lateral stress value, we need to multiply the linear with the Poisson's ratio. So we are multiplying the linear with the linear is something which is longitudinal, right? We know along that length. Okay, so we are multiplying the linear value with the Poisson's ratio. So this is how we got the E1 value. So E1 is equal to sigma 1, we know, PD by 2T. We are writing here in the denominator. This is mu into, this is PD by 4T and E. We can take common PD by 4T or 2T. Here we have 1. This is mu by 2. Okay, we can also write mu or 1 by m. We know Poisson's ratio can also be written as 1 by m. So this equation might be PD by 2T into 1 minus 1 by 2m. This is our circumferential strain. The second one, longitudinal strain. Longitudinal strain, which is E2. Okay, the same way E2 can be written as sigma 2 by E minus mu into sigma 1 by E. Same concept again. This is our linear stress. Mu into lateral, again I show you here, mu into this linear part. So this is our sigma 2 by E minus mu into sigma 1 by E. We know sigma 2, which is PD by 4T E minus mu into, this is PD by 2T E. We can take common PD by 2T E. So this is 1 by 2 minus mu, and I already mentioned mu can also be written as 1 by m. So longitudinal strain is equal to PD by 2T E into 1 by 2 minus 1 by m. Okay, in adding to this 2, we also have volumetric strain, because the effect we are talking about, the dimensions on the cylindrical walls due to internal pressure may also cause change in the volume. So that is volumetric strain, some EV. Usually a strain can be written as change in dimension to original dimension. So we are writing as change in volume to original volume. This is basically what is a volumetric strain is. The volume of a cylinder can be written as pi by 4 d square into L, right? This is the basic formula for volume or strain. We can also write as change in volume to original volume. That is what our strain definition defines as change in volume to original volume. Change in volume can be final volume minus initial volume, which that is what change is, by initial volume. Original volume means the initial volume part, but the volume which is initially is pi by 4 d square L. Now we'll see the change we got in the volume. That means the final, this is our initial value, one thing. The final volume which we can get is pi by 4. There is some change in the diameter, which is some delta d. We have a square. The same way length, we have a change in the length, which is delta L. If you see pi by 4 into, this is a plus b whole square, a square plus b square plus 2ab. That means d square delta d square 2d delta d into L plus delta L. Now we have multiplication, say d square into L, so d square L, d square into delta L, so d square delta L, delta d square into L, delta d square into delta L, 2d delta d into L. The same way 2d delta d into delta L. We multiply things, right? We know delta L is a very small thing. That means delta L can be delta L or delta D. The delta itself change, it's a very small thing. That means 0.001 order thing. If you see, if we have delta D square, if delta D is 0.001, its square can be 0.00001. Then if it is multiplied with delta L, it can be 0.000000. So what we are doing is we are eliminating some basic or we are eliminating some simple or easy terms. That means this can be eliminated because it is a very small term. Now you see again, this delta D square is also can be eliminated in the same way. Here you have delta D into delta L, so this term is also eliminated. So the remaining terms here we are having.
Playing from desktop 8C4 is.
So the remaining part which we are having, or the remaining thing which we are left here, is the final volume pi by 4 into d square L plus this d square delta L plus 2d delta D L, right? This is our final volume. So to find the volumetric strain, what we need to do? Final volume minus initial volume by initial volume. This is our final, this is our initial. So we should minus final minus initial by initial. We'll see. So EV is equal to final volume, which is pi by 4 d square L plus d square delta L plus 2 dl into delta D, 2 dl into delta D minus, this is final, initial is pi by 4 d square L by, again the initial is pi by 4 d square L. If you see, here you have a pi by 4 d square L. If you multiply, here you have a pi by 4 d square L, here you are having a pi by 4 d square L. That means if you take pi by 4 d square L common, here you have pi by 4 d square L plus, this is some minus. So both this pi by 4 d square L minus pi by 4 d square L gets cancelled. So you will have d square delta L 2 dl into delta D by pi by 4 d square L. Will divide the denominator part. See, d square L plus 2 dl. You're having a pi by 4 part, sorry. We are having a pi by 4 part, right? That pi by 4 can be cancelled here, so we are not having pi by 4 again. 2 dl delta D by d square L. D square cancel. L d cancel. Here we have delta L by L. Here we having 2 delta D and 1 d delta D and 1 d. This is our longitudinal strain. This is our circumferential strain, because this is along the circumference, this is along the length. So we have EV is equal to a relation which is mentioning E2 plus 2E1. We already know what is this E2 and E1s are. We have an equation for this, PD by 2TE into, this is 1 minus, sorry, this is 1 by 2 minus 1 by 2 minus mu. Here you can see this 1 by 2 minus mu, or in the terms of 1 by n also you can write, plus 2 into PD by 2TE into 1 minus mu by 2. This is for circumferential and this is for longitudinal part. Again you can take common PD by 2TE value. We have 1 by 2, we have mu, we have a 2 here, 2 into 1 is some 2, and we have some 2 into mu by 2 is again some mu. Okay, so PD by 2TE into this 1 by 2 plus 2 is 5 by 2, minus mu is 2 mu. So we have a formula is 5 by 2 minus 2 mu. This is EV is equal to PD by 2TE into 5 by 2 minus 2 mu. This is what basic concepts of thin cylinders.